All right, so just a quick reminder, right? All the stuff that we talk about is in the modules. I even tried to, at a certain point, start putting the dates in so that you get a sort of timeline and you can go back and forth as needed to sort of refer back to things, okay? So anyway, chronological record here, 3rd of September, that's today. More points, lines, and curves in Grasshopper. And then we also have a new assignment called Your Truss System. Right, so this was what I was just showing, but again, when I'm recording this, as soon as this recording will be up here momentarily after class, usually takes a little while to upload to YouTube. Then I'll actually be able to embed it before it's even done processing. So you might see a sort of a gray box here for an hour or so before it processes. But anyway, here are the example files we dissected and annotated today. So these are the files I'll be opening and closing, building in front of you. Again, just try to be in the moment, pay attention, right? Pay attention, that's what I recommend. Where every little tool or box is, that's something that you just learn with practice, right? You're not gonna get that from just a quick demonstration in class. What I want you to do is start to think parametrically, start to understand step by step, what are we doing, right? And how one output from a widget becomes the input or ingredient for the next step, right? Okay? Just like if you were manually modeling something, making it out of chipboard, or virtually modeling something, let's say in Rhino or Revit or something, or drawing it at your desk, right? You know, there's steps, there's ingredients, and then you start to build, construct. It's the same thing with digital technologies, right? So let me just go ahead and open up Rhino, and we'll go ahead and get started. And I have my mouse already ready, readied up. Why does it keep doing this? Really, stop it. Here we go. Just waiting on Windows here. There we are. Okay. So I will give you a sneak peek of what we're going to be doing over the weekend, right? You'll be making some sort of truss system like this, right? A set of trusses. Then we'll start to take different perspectives and other sorts of drawings of these things and exporting them out quickly, right? It's just sort of the raw assets that we can then start to use for collaging in Photoshop next week. Okay. All right. But first, let's start simple. Next, new, don't save now. All large objects feed, sure, why not? All right. And again, I'm just going to go through this. Column grid example, Grasshopper file. All right, let's do that. I'm going to go to tools really quickly and turn off this annoying grid. I hate this grid. I can't stress that enough. Like visually, I just find that grid just awful. All right, so I'm typing in Grasshopper into the command line to open up our Grasshopper plugin. And as you discovered over the weekend, right? You can save Rhino files, and that has Rhino geometry in it. You can save Grasshopper files. That basically just keeps this mind map of all the sort of nodes and rubber bands connecting the nodes, right? If you're generating geometry in Grasshopper, you see a preview of it that's dynamic, not static, dynamic in Rhino, right? It only exists as long as Grasshopper's existing, right? And sort of processing things. And if you want to bring a static version of the geometry that you generated in Grasshopper out to Rhino, then you bake it into Rhino, right? Okay. So we'll talk about that here in just a minute, but let me just go ahead and open up one of these example files where downloads. There we go. No, documents. Teaching. Always 16 clicks away. Here we go. Example files for September 3rd. Perfect. Column grid example. Not unlike some of the stuff that you looked at the very beginning. Let's see. Here we go. Okay. So, I'm well aware that there are particular grid tools, right? You can just sort of place a grid widget and tell it the spacing X and Y, and it'll make the grid for you. But what I really want you to come on in, we're just getting started. Get settled and just watch. You don't have to set up your laptop or anything. All right? So, but what I wanted to sort of talk about is that oftentimes you find yourself actually having to make a list of ordered numbers. So that's why we went through the process of actually making our own X and Y coordinates to plug in to make points in order to make a grid, right? So really important. We have series and we have range, right? Two different methods. Range assumes that you have a minimum, maximum, and you tell it the number of steps in between, and it generates those numbers. Series assumes that you just have a start number, and then an increment after that, and then a number of increments, and it generates that list of numbers. Very, very important. I can't stress this enough. You'll find yourself always going back to this. How do I make a list of numbers? Maybe it's the widths of or lengths of beams, etc. And it comes back to how do I do that in an ordered way? These are two really common tools. In this case, we use series, and so we give it a start point, in other words, 0. We tell it the spacing, in this case 18, and then the counts, right? 8. And lo and behold, we get 0 to 126 in increments of 18, right? Yeah, 18, 36, 54, 72, as one does, right? We can think about this now as being sort of creating X and Y coordinates that we can plug into a point widget, right? Did the data matching make sense to you guys? Kind of weird, right? It's a little bends your brain a little bit, right? But this idea that we make a list of numbers for X coordinates, a list of coordinates for Y numbers. If we plug them in, X and Y, they'll match the first X with the first Y and make a point. They'll match the second X with the second Y and make a point. If we want to make a grid of points, then we have to do something called cross-reference, right? So we have to cross-reference every single one of these numbers, 0, with every single one of these numbers. So 0 to 0, and then 0 to 18, and 0 to 36, and 0 to 54. And then finally we get through that list, and then we go, okay, now we have 18. 18 to 0, 18 to 18, 18 to 36, 18 to 54, etc., right? So it's this idea that when we get this out, we get 0, 18, to all the way to 126 repeated over and over again. And here we have zeros, 18 of them, and then 18s, and then 20, etc. All right. So we get a set of points. And of course, once we set a grid of points, we can actually make those mean something, right? In this case, making a column grid. So I just added a box widget. The inputs are, they'll point to make a box. So if we give it 1 point, then it'll make 1 box. If we give it a list of points, it'll make a list of boxes, right? In this case, all we have to do is give it an X and a Y and a Z dimension, make it tall, and suddenly we have columns, right? All right. And again, information moves from left to right, so I can adjust the spacing or the number, and everything sort of propagates from left to right. We can change the height. And of course, I can double click and change minimum maximums in each number slider if I want to sort of give myself some more freedom or flexibility. Right. Okay. The reason I'm pointing this out, and it seems kind of obvious at this point probably after what you did over the weekend, is we're going to build on this. Now, instead of making a column grid, later on we're actually going to make a grid of points and build a surface along it, right? So keep that in mind, right? Just sort of take a mental picture of this sort of grid of points with lines projecting up in Z. All right. Let's go ahead and close that one. Nah, I don't really need to change. Save changes. And what's the next one? Ah, spider points. Perfect. What a weird name too, right? Spider points. What the heck is that all about? All right. Now you'll notice that, let's just, again, in the spirit of being able to create graphs in Grasshopper, I think it helps to be able to look at existing ones and sort of read through them. Is that big enough for everybody to sort of see? Let me get my cursor out of the way, and I'll just highlight that in green. What does this one do? Populates a two-dimensional shape with a set of random points. How many points? Well, there's an in parameter, so you can set that. I think my default is set to 100, and so I think if you counted these, there'll just be 100 in here. There's also something called a random seed. I can give it a whole number between 0 and 10, 0 and 9, something like that, and that'll give me a different sort of list of random numbers. Random, actually they're pseudo-random, right? Random implies that every number has an equal chance of being picked each time you pick a number. This is simply trying to simulate that randomness through sort of seeding. So, and then of course R stands for rectangles. I can draw a rectangle in Grasshopper to define that area and then to populate with When I get out of that are points, surprise, and I can take it to this next widget, which looks at a set of points and ask yourself closest points. So this is interesting. This says find the closest points in a point collection. All right, well, that's interesting. And then what we'll do is we'll start to draw lines. But look over here, right? I think hopefully you guys noticed this, and now it's become a little more familiar to you. Right, we have a curve widget over here that's orange, meaning it doesn't actually have any information inside, right? So we need to give that's orange is a sort of orange flag, literally, for you to sort of say, oh, this needs information. Once I do that, then the rest of it should work. Right? And CRV is short for curve. That's probably what it wants, right? So let me just quickly draw a curve through this rectangular field of points. And I'm just going to quickly just make a sort of Bezier curve, control point curve. I'm going to turn off my object snapping. Now, by default, turn off my ortho. By default, of course, in Rhino, just make something goofy like that. Let's say I'm following some strange, crazy topo or something. Again, by default, if I just have all my object snaps and stuff turned off, if I'm drawing in that perspective view, it's going to put everything on the XY plane was equals 0, right? And sort of keep it nice and flat for me. All right, so now let's take a look. I'm going to basically, again, right-click and set this curve and bring this curve in from Rhino into Grasshopper and start to build off of that parametric, right? Okay, but let's see what it's going to do first. First, I'm going to plug that in, and I'm going to say, let's evaluate that at a t parameter. I don't know how much I explain that in those videos, right? But if you think about lines and curves, we can get, the most helpful metaphor I can think of is thinking of a street or a road, right? Streets and roads, they can be straight. Sometimes they have to curve around mountains, or around water, or underneath mountains and tunnels, etc., right? But again, if you think about having just two directions, forwards and backwards along a line or a curve, right? Tropicana, for instance, or Maryland Parkway, right? Along Maryland Parkway, we have a series of coordinates, right, called street addresses. So UNLV's happens to be generic 4505 South Maryland Parkway. I just know that because it's the address from my office. 4505 South Maryland Parkway. And so that's basically a coordinate system along, right? Presuming that at some point we get to 0, and if we go further south along Maryland Parkway, the numbers just get bigger in size. So it has a minimum and a maximum, right? And we can think about any curve having that sort of minimum maximum and be able to place an address along that called a t parameter. Okay, so that's what this parameter is. What we can do is we can plug this curve in and then re-parameterize it, normalize it, so that the starting point is 0 and the end is 1. That makes it very helpful for us to start to understand. Let's say we want to snap to a midpoint. It would be, our t parameter would be 0.5, right? Or if we wanted to put things quarters along this, we'd say 0 and 0.25 and 0.5 and 0.75 and 1, right? And we'd start to populate this thing with points, with t addresses, right? So what I've done is I've made that a parameter so we can slide it from 0 all the way to 1. Now let's go ahead and set this curve. There we are. Oh yeah, look at that. Okay. I'm just going to turn this off. And you can see, let me just click this point. Hopefully you can see that green point, that it moves along the curve as I move the t address, right? All the way from 0 to 1 at the very end, right? One end to the next. 0.5 would be the midpoint along the length of that curve, right? And so anyway, what I'm doing now is I'm taking this point, I'm measuring it, and trying to figure out of this cloud of random points that I've made, the 4 or 5 or 6 closest. And then I draw a line from that, what we usually call an attractor point. It attracts. We're looking at distance from that attractor point to the 5 or 6 closest, right? So in fact, I can change it here. How many closest, right? So let me go ahead and turn this on, right? And this is why I call it spider points. Because as we do this, you can see that again, everything's sort of calculating in, so in other words, as the point moves, the closest points, the set of closest points changes, and we continue to draw lines to the closest points. Right? So I found that this is actually a helpful way to sort of make this stick cognitively in your head. Right? Just think of spider points. Not to be confused with Spider Pig. Anybody see the Simpsons film a long million years ago? Okay, anyway. I just dated myself. That's all right. I feel like a moron now. Okay, so that's spider points. Right? I can't believe I just recorded that. Darn. All right. Shoot. All right, scissor example. All right, so what I like to also think about is, for instance, how these things might help us actually fold things, right? So, in fact, we'll actually be looking at that in Project 2, where you make these sort of folded paper components that will then build in Grasshopper, right? And then actually instantiate, and then you'll flatten them out, laser cut them, assemble them all back together as a physical prototype. But one of the key things I think to think about here is that it's kind of not a trivial thing to make a set of hinges where the lines move reliably, or edges. Let's say we're looking at a piece of paper folding in section, without things actually stretching, so keeping the right dimensions. So if you think about this, this is actually just the most elegant little geometric trick I found when it comes to doing this. Open document, scissor, there we go. And interestingly, let's see, I need a curve. I don't need a curve like this though. I'll just make a line. And I'm going to set this curve. There we are. All right. And what I've done is I've made it so that we can actually make that hinge without the curves actually stretching. So that the actual full inflection points move in and out with it in order to make sure that we're not doing anything that resembles science fiction, but actually embodies a physical environment. Here's how I do it. If you think about this, I love this. I'm basically just sliding two circles along a line. And those lines that I'm looking at as the edges are just radii of the circles, drawn from the center point of each circle to the point where the circle intersects the next circle. So the radius never changes, and therefore the lengths never change, right? Beautiful little piece of geometry there. Now, it has real implications if you're trying to, again, simulate actual materials that can't just stretch or shrink, right? But actually, have a set of atoms going in either direction, and then suddenly you have to sort of compensate for that, right? All of this is just simply, look, just taking a line, and what do? I plot a point along the line, right, with this slider. You can go from 0 to 0.5, 0.499 actually. Right? Then I take this exact same value and I subtract it from 1, and I use that for another t value for this one, so that it goes from from 1 all the way to 0.5001 or whatever it would be, right? And so that way, when one's moving in this direction, the other one's oscillating in the other direction, right? Then I can just draw circles. Then I can find where the curves intersect. That gives me a point, actually gives me 2 points, and I can easily draw a line from the center to each of these points. And voila, right? Oh, yeah. I love it when a plan comes together. Very, very simple. All right. Don't worry, we'll build up. All right, how many of you guys like roller coasters? Yeah, pretty cool, huh? Yeah, I used to love thrill rides, and I haven't gone in so long. I'm not sure how I would do these days. Getting old. All right, open. I'm going to open up a Rhino file, I think. Here we go, roller coaster example. There we are. All right. So what I've done is I made a curve that it sort of changes its direction in all three axes, right? Sort of volumetrically fills the space, right? So the way I generated this, let's say if I just went to plan view, well, you can see actually it's quite simple, straightforward curve and plan. I'm just going to make one myself. If I go ahead and click these, again, they're non-uniform rational B-splines. They have knots and weights, and I can always resculpt this curve by selecting the points that generate its geometry and stretch them around a bit, creating, again, almost like it's a clay curve, if you will, and start to make something three-dimensional. All right, so there it is. And so it kind of resembles a roller coaster track. Roller coaster tracks are really good at this. In fact, manufacturers of like roller coasters, but also like ship hulls, right? Things, automobile bodies, right? Things that have lots of compound curves are complex due to either looking at physics in motion or aerodynamics, etc. Right? So, or maybe even like a structural performance. When you curve something or doubly curve something, it gets a little stronger, more crush resistance in places. So, anyway, what I'm going to do is I'm going to go ahead and bring this in. Let's see, open roller coaster example. Aha, yeah, very simple, straightforward here. So what am I doing? I'm bringing this curve in from Rhino. Here's my curve widget. It's a little placeholder geometry. And I'm going to bring something from Rhino into Grasshopper and use it for something else. I can. It becomes an ingredient for similar to the divide curve widget. Okay. This one divides the curve n number of times, in this case 46 times. And at each of those points, it puts a perpendicular plane on the curve as well. Let me just show you what that looks like. So if you think about this just for a moment, right? Remember calculus, and it was all about how the curvature of curves change over time? Like parabolas, or hyperbolas, and things like that, right? That's what it was about. You're welcome. And can you believe that Isaac Newton invented calculus during the pandemic, sort of holed up in his room when he was like 17 years old or something? It's ridiculous, right? A bizarre thing. Hopefully you guys have lives and anyway. But then again, yeah, anyway. So, if you think about curves, particularly as it curves through 3D space, right? If you look at the curvature of this, it's constantly changing. It's constantly in flux as you move along that t parameter, right? And so oftentimes what we would do is we would sample the slope of a curve at a particular point, understanding that that tangent line, the slope, would change as you move along the curve. And all the perpendicular plane is the plane that's perpendicular to that tangent at any given moment along this curve, right? So if I, for instance, turn this off just for one moment, let me just make a new document, and I'll just bring this curve into Grasshopper again. There we are. All right. And I can quickly demonstrate this. Let's see. I'll analyze the curve at a t parameter. Let's see, where is that? Why am I not seeing that? There's perpendicular frame, horizontal frame. Am I just silly, like it's right in front of me or something? That's right here, t evaluate curve. All right. Huh. Yikes. All right, so I'm going to go ahead and make sure that's reparameterized. That way we normalize it from 0 to 1. I can use this number slider without really having to change a darn thing and move it, point along it. But what it also gives me, besides the point at that t location, is also the tangent vector of the curve at that t location, right? And so if I created a line really quickly using this as the start point and this as the direction, and I gave it a little bit of length so we can actually see it here. Let's see, let's go. Let's go, here we go. All right. Then I can actually move this around. And of course you'll see that the tangent moves around with it, right? And in fact, if I do the same thing down here and actually populate this with also a plane at the exact same t parameter simultaneously, then you can see that again, that relationship, right? The perpendicular relationship between perpendicular frames or planes and tangents, right? Really important because if you can understand it with curves, and then you think about a surface that has three-dimensional curvature, right, as basically having a u value and a v value, basically two curves with two tangents. If you can pass a plane through those two tangents, that's how you get your tangent plane. Right? So anyway, some things to think about. We'll get there. Like I said, that's project 2. Let's stick with project 1. Where was I? Oh yes, off on this little adventure over here. So all I'm doing is populating this with perpendicular frames. All of these are planes, and so in fact, the tangent to the curve is actually the z vector for the plane. We have an x and a y as well, right? You can see that, right? There's x, there's y, there's one or the other. We can deconstruct it and say, here's a list of planes. Now I'm going to have a list of origins in x values and y values and z directions, right? And I can pass those to lines that then draw and basically three-dimensionally offset this curve, and then find their endpoints and then connect them all together with an interpolated curve to draw the second rail, right? Sort of track. Right, so again, I show this not because I think roller coasters are neat, but because geometrically this is significant in how you can begin to build, right? You can take a point or take a curve and start to build. It becomes a scaffold to start to create more geometry that's deeply informed by some parameters that can then be adjusted as you start to learn more about the constraints of the project, as sort of fuzziness of your ideas start to hone in on clearer and clearer constraints, right? Then we can start to regen very quickly just by simply moving some numbers around. All right, that was the roller coaster example. Let's see here. All right, reactive surface with an attractor point. This is where that grid and the columns start to come into play. All right. Did you guys already watch a video on this or no? Doesn't ring a bell? Like the surface that moves around? Oh, I already showed you guys this? Oh, shit, okay, whatever. No? Yes, no? All right, well, we'll go over it really quickly. Because what we'll do is we'll generate a surface, then we'll start to build trusses along the surface after that. But we'll make a surface that we can change the shape of with just some simple sliders. Okay. Again, talking about attractor points. This idea that, again, then we'll talk step by step through the process of what you'll be going through over the weekend, where you build your own surface, populate it with your truss system, and then start taking some perspectives of it. All right, so, yeah. Let's see here. Do we have a Rhino file to open? Probably not. No, I guess we do. Here we go. Yeah. Oh, because I have a curve. Yeah, I've already drawn. Sorry, each one of these has the stupid grid on. Have I stressed this enough, how much I hate that grid and how it just makes my eyes hurt just looking at my screen? All right, so just going to move this stuff around so Grasshopper and the Rhino preview can coexist a little better. There we are. Okay. And I'm just going to open up the Grasshopper file. Again, these are posted on Canvas in case you want to take a closer look at them. Need to refer back to them or see something that I did. Reactive surface with tractor point plus trusses. Okay, there we go. All right, so here's what we're doing. Let's take again, in the spirit of looking at Grasshopper graphs and trying to read them. First thing we're doing, this looks strangely familiar from earlier, right? Making an ordered list of points. One here, list of numbers, and then we're putting them into cross-reference in order to generate x and y values that can be plugged into a point widget and create a grid of points, right? So it's similar to before. Now, again, just like before, I'm bringing this curve in from Rhino, and I'm evaluating it at a t parameter, and I'm generating a point. And then what I do is I measure the distance between the attractor point and all of the grids and points in the grid, right? And then I use that distance, and I use it to make a height, right? So in other words, I draw a line from each of those points in the grid, and the height of that line, or the length of that line, is governed by the distance each of those points are from the attractor point. And it gives me this shape, right? So obviously, the point's closer to these points, and as a result, so is the surface, right? And they get longer and longer the further away the point is from the attractor point. And The attractor point, remember, is just one location along many possible locations along that line, and I can change that location and thereby change the shape of the surface, right? Okay. And then, of course, when I have a grid of points, I can just simply make a surface from a grid of points, right? Like it sort of interpolates across the grid of points. All right. There we are. And now, for the real finale, maybe, populating that surface with a set of trusses, and then, of course, remembering that, where is the surface? There it is. Turn the preview off there. And then remembering that as the surface geometry changes, then all the trusses would in real time as well. There we go. Something kind of satisfying about seeing that. All right, so again, what it begins to talk about is that we can actually make a surface, right? Let's say the facade of a envelope of like a glass envelope of a building, right? Where we have to use maybe cable trusses to hold up the instead of using mullions, the spider clips to hold the glass in place. Or we make a roofscape, and then we can actually populate that with trusses to sort of span from one end to the other. Right? It's a pretty common problem. I mean, you know. So anyway, yeah, I don't know, just saying. So anywho, there we go. And let's say that we wanted to change that shape. Now I'm just showing you how you can change that shape. This is just a really common way of showing people how attractor points work, making grids, tying these things together. It's like I learned generative components 20-some years ago with this similar sort of exercise. But what I wanted to show you is how you can do that with your own surface. So here, let me just open up. Let's see here. Let's open. Let me think. Where is it? Open, reactive surface, project 1, truss space. Here we go. Right. Okay. Just turn this to X-ray for a moment. And let me just turn a few things on and off. I've baked some things in from Grasshopper already. Just turn that off. So this is what I did. And then you can see in Grasshopper, oh, come on. Let's just turn this stuff off. Close it out. Let's see here. Recent files, trusses along rails. There we are. Oh, yeah. Look at that goodness. Yeah, it's getting a little more complex, right? A little longer. And we have to worry about something called data trees in this case. So what I did is I made some sort of envelope that's sort of 50 by 500, right? So it's sort of a 10-to-1 ratio, aspect ratio. So I wanted something with a lot of depth to it for our perspectives and things like that, because we're going to emphasize one-point perspective for this. And then what I did is I simply, in plan view, let me just blow this up a little bigger. Let me just highlight this. There we go. I drew a curve, right? It's a flat curve. It's just stuck on the XY plane, because I drew it in top view. Then I just mirrored it to make a copy of it, right? You can see it here. And I moved that up in Z. So as you can see, I have this curve, and my original curve is still on the XY plane at the sort of ground, right? I just had two frames, rails. So a bottom and a top, just like I did before. Instead of actually locking those into a surface, here's what I did. I just simply divided them, and this is what I think you guys can do then. I just simply divided them. Let's see, where is the divide? Let me just expand this out a little bit and show you. I don't know why I didn't just show this instead, but whatever. Okay, so here's one curve. Here's the second curve. Okay, there we go. So essentially, let me just turn this on and off so we can actually see them and build it together here. Dispatch, preview off, preview off, preview off. Oof, how embarrassing. Oh well. Okay, so here we have two curves. I'm basically dividing those curves up, using the divide tool, but with the perpendicular frame, so that we actually get the perpendiculars. Then I'm simply connecting those two, each of those planes one to one, right? A list of, they're actually a data tree. I graphed them right here. I right-click and say graphed, and that turns them into a data tree. You can see that the rubber bands are there, right? So you see how they have this up arrow, and I've grafted it into a data tree, right-click, and graph the output. Now suddenly I have a data tree of lines, right? When I plug in start data tree of start points, data tree of endpoints, and then I simply build these things from here on out, just like I did before, right? Here's a T parameter building a frame, right? Here's the line that I build off of it, start point, direction, length. Where's the length? It's here, right? I can make these, bigger or smaller. Then I find the endpoints and connect them up with an interpolated curve, right? Okay. The number of divisions is back here, so I can make this more or less dense. Then I divide all of these with points, and then start to play the game of connect the dots, right? So I start with just the regular, just a sec, I'll call on you. The regular list of curves and the bottom list of curves. Then I shift the lists once and twice, connect the regular with the shifted with the regular, right, in order to create the cross bracing, the cross webbing. At this point, you don't really need this. At this point, then I can take whichever curves I really want to keep and start to pipe them, right? In other words, give them a radius and then sweep a circular section across them, right? To give the struts actual thickness and make them a polysurface. And then at the bottom here, you can see that in another sort of line of thought, whereas I wanted these sort of lines, these vertical lines that I drew in that 50 by 500 foot plane to sort of reinforce the 1-point perspective. I didn't want to just draw a set of regular horizontal lines that sort of move back in depth. So what I did is I actually used these planes back here, got their x direction, started to draw lines that actually start to mimic the normal direction of the curve at each one as it goes through. So you can see that, like in top view, for instance, that instead of a regular grid, it's a sort of conformal grid that sort of morphs along the curvature of the curve. Okay. So what I'll do is I'll go ahead and post this on Canvas so you can have it as an example as well, because you want to follow this one. The surface one, for whatever reason, the logic is defying my brain this morning, okay? But I'll go ahead and upload this one ASAP, like right after class, okay? As well as get the video uploaded. Now, I did also want to talk, first of all, you had a question really quickly.
Yeah, I was saying like we don't need to use the line, right?
A little louder.
We don't need to use
Yeah, so don't make a surface. Go ahead and just make a bottom and a top, and then you're starting to divide things up, so you just continue with the curves. Yeah.
Before, can we use previous Grasshopper files for like other layouts of the Grasshopper that we imported in this assignment?
Maybe, I don't know what you mean, but I really want to see trusses, and I want to see 500 feet long corridor of trusses.
Yeah, we have done 2D trusses before, and I'm just saying if I divide the curves into lines and I import the...
Oh, yeah, that's fine. That's fine, yeah. Yeah, no, that's cool. But again, make sure you're following the parameters of the assignment so that we get some things out. And I just want to talk about that now. What do you get out of this, right? I don't necessarily want to see a Grasshopper file from you, right? But in this case, what I've done is I've taken these pipes and some of these lines and I've actually baked them into Rhino. So you can see here, let me just turn this off. You know, I've baked the trusses into Rhino, so now I have them and I can render them. I've baked these lines in, etc. Right? So in this case, what I would recommend you do, because we're just doing photo montage and collage, in Photoshop with these, is to simply turn on the rendered mode. And what we can do to get PNGs out is simply use the view, pull down, capture to file. Right? When I do that, it'll give me this box and I can say, yeah, just keep the scale, or if it's really small, this is 1130 by 524, maybe I say scale it up by 2, suddenly you'll see the pixels will double, so you'll get a higher resolution, let's see, 2. Right, so now it'll be 2260 by 1048, etc. Anyway, when I hit OK, make sure the transparent background set. I can save as a PNG file. PNG is important because it preserves the alpha channels, the transparent background. The JPEG won't, it'll flatten and give you a background again, which is unfortunate. And then also to say that you can play around with your display modes a little bit. And again, I can go over this more again on Monday if need be. But first of all, you know, the right-hand side here, I have something called named views. If you just right-click, you can usually toggle on what you want to see in this menu over here. Look for the named views, this little camera icon. But this will allow me to, once I have the perfect view set up, to save the view, hit the camera plus, change it, and let's say this is perspective 04. Then when I can go back and forth and get the exact view that I want. If I've taken some time to really craft and take care of where the camera is, then I can save that and always go back to it and take a re-rendering out. In this case, you'll notice, again, this is why I thought maybe we're running out of time. We are starting. So this is the example just from the Rhino preview, right? So I select those widgets with the geometry that I want to bring back into Rhino, and I said bake. I put them on a particular layer, and then they won't look like this anymore. But when you just open them up in Rhino, you know, you can turn the render mode on, they look like this. Then I did a few things. I turned the ground plane to black. I kind of wanted some contrast with the sort of, you know, like white clay is cool, but when everything's the same color, it looks really, it starts to trap you. So I changed the ground plane to black and then changed the line work to white and started to take some different renderings out. You can see again the sort of transparent background here, ready to be played around with in Photoshop. And that's the way to think about this as a sort of composite drawing. Let me just show you how I did that. If you go to the render settings, which is the blue sphere, first of all, I have ground plane clicked on, and then it says show shadows only. I click it and say use a material, and then I can simply make a new plaster material that's black, and then suddenly that shows up. And then sometimes the layers that are black won't show up, so you can change the layer color to white, and then you can get these curves to show up, right? So you can play around with your display modes. Think about how these things work. Last, you know, if I'm taking let's say I'm taking this as one of my perspectives, what do you notice about this? It drives me crazy. What do you notice about this? Like the frame of this? Half the goddamn architecture's off the frame, right? Yeah, exactly, right? Like it drives me no end. I can't see the top of that, especially if I'm here at the end, right? So one of the things that I do, and I usually can plug into a super, it's one of these, but just a monitor, is I'll change the aspect ratio of my viewport to fit everything in. If I'm just simply doing that capture thing. Then what I can do when I do the capture is, you know, this is actually quite small now. It's 676 by 847. So maybe I turn it up in scale by, let's say, like a factor of 3. Now it'll upscale and add that information, the pixels in, for a 2028 by 2541 size, right? So, and that's what I would say. Try to make sure that the longest dimension is at least over 1800 pixels, right? You just want to have something with decent resolution. There's nothing worse when you show something and it's pixelated and it looks like garbage, right? Like you lose credibility instantly, right? Like everybody's like this is your tool, but you don't know how to use it, you know, that kind of thing. So just keep that in mind, right? Okay. All right. I know